Today we're going to continue on our quest into thermodynamics, now moving on from the first law and talking about sort of heat and work, or processes we've talked about now. Now we're moving into entropy, which is the second law. This is the second sort of thermodynamic principle and term that we're going to discuss today. And this bridges over because, we've learned a lot in terms of, okay, we have these processes. The processes can happen. There's a heat exchange or work exchange involved in that. That's energetic content. Last time we introduced this concept of Hess's law, right? This is this ability to say, look, it's a transitive property logic test. If I know the difference between state A and state B, and a difference between state A and state C, I can calculate the difference between B and C, an unknown between two. So it's relating one change and a second change to this third unknown change. And it's basically this kind of almost a linear algebra kind of problem to put this together. So we're going to practice this a little bit more and move on to this next part. So where we left off, as I mentioned, we introduced this concept of Hess's law. And if we were using it, we were using these delta HF values. What was a delta HF? What was the name special that we've got that? Delta HF is referring to, delta H naught F is referring to what? Yeah, the enthalpy of formation. Right? Now, what was the definition? What did we say was an equation describing the enthalpy of formation? How do I state that roughly? What are the stuff that you need to talk about enthalpy of formation? Yeah, it's the energy to make a molecule in its standard state from elements in their standard state, right? So if we looked at something, let's look at this guy here, and we're going to talk about just, let's say, CO2. If I want to know the equation which described the delta H naught of formation for CO2, what would that balanced chemical equation look like? If I was asked to draw it out, what would I need to describe CO2? So to make it, I'm going to need what elements? CO2 is made of carbon, right, and oxygen. And remember, it's elements in their standard state. So let's say I'm going to do CO2 gas, that's fine. I'm going to need carbon and oxygen, a little bit more than that. Okay, I need a certain amount of carbon and oxygen. I'm going to need 2 oxygens, 1 carbon. But how do I find what's the normal distribution of these two? Carbon exists as what? It's not just carbon. It's not just carbon solid. Yeah, it's carbon solid as graphite, right? It's how you would find that element normally. Oxygen doesn't exist as oxygen. It exists as O2. That's right. It's going to be O2 as a gas. So it's the combination of solid carbon, one of them, and 2 oxygens, or in this case O2, gives me my part here. So this is the balanced chemical equation describing the elements that I need in their standard state to form this compound. And that from that, this would have a delta H naught F value, and that's a number where we'd have to actually look it up. It's going to describe, this is something we find in a table somewhere. But again, diagrammatically, what we're kind of saying is it's taking elements in their standard state, and usually we're forming molecules off of it. So if we have the same elements to make a different molecule, same stuff, the same cloud or building blocks of all matter, having these elements in their standard state allow us to have these values. Let's say it's the delta H formation of some compound, formation of some compound, a different hypothetical reaction, delta H formation of a different compound. It means that I can now talk about this difference here, something that is related to this common standard state up here. I can solve this delta H of usually a reaction, in that case, RXN. So we're using these values to sort of calculate between the two of them. So in this example, we've been given this equation. We do not know the delta H of this reaction, but we've got delta H's formation. We can calculate it. So what's the stages that we do? So again, I'm just going to open this part up. You guys tell me what the value is. And as a challenge, we're only going to leave it open for about a minute. I'll tell you why doing this quickly is a possibility. Okay. If you're asked to draw the chemical equation, get balanced chemical equation of formation of something like CO2 or COCl2, then yes, you have to specify the starting material would be carbon, monatomic, solid, and graphite. You need to specify which state you are referring to. And remember, the reason why is because some elements have different allotropes, they have different sort of molecular forms, so we need to specify this 2-point. Okay. Now I'm going to cut it off. I know a lot of you haven't probably finished this calculation, but again, we're going to do this. I want to sort of highlight a specific piece of this. So on this, if we first of all looked at this, what's the general equation that I need to use here? What am I going to do in terms of setting up this thing? Generally speaking, I'm looking for the delta H of this reaction. So what am I going to have to add, subtract? Yeah. The sum of all the products, where you get to, minus the sum of all the starting materials. It's your final state, all the different delta H's of formation with their right stoichiometry, and the delta H's of formation of your starting materials. Final minus initial. So based on that, we're going to do this whole part here. Is there any of these, A, B, C, D, E, that you're going to like, no, that does not make sense. The number numerically looks wrong. Yeah, A looks weird. Why? If you had to sort of contextualize that, why would we say A is, well, it's huge, yeah. If you look at your values or your delta H's formation, they're all negative, right? So we're going to take a sum of negative numbers and subtract some other negative numbers. There's no way that we're going to get this huge thing. The magnitudes don't seem to make sense. So yeah, you're like, that's not too small. The magnitude is very large, put it that way. But yeah, A looks weird. You can flag that as a problem. Do you think this is going to be positive or negative? If you look at this guy, if you had to sort of look at what you would expect based on where you're going, where you're coming from, what does it look like, positive or negative? So we got a little balance. Now again, what are your two products? It's COCl2. The energy there is minus 223, and water minus 285. So call it 200 and 300, about 500, right? Your starting materials, one of those is 400, and then you've got two 90s, right? That's actually pretty close. Like again, if you look at the actual magnitude, 400 plus 2 times about 100, that's about 600 on the starting material side, and about 500 in this thing. My guess would be we're looking at a positive number, right? Just from that point. But even doing that exercise up front, based on the numbers and the setup of what your expectation is, it helps you sort of do that quick gut check, right? Okay, so we're going to finish off this actual calculation. If we're doing this out, we're saying it's the sum of all my products and sum of all my starting materials. So putting this off, how we've done a reaction, this is 223.0. That's the heat of formation of CO2. We need 2 times the heat of formation of our HCl. That's minus 92.3. So it's these two guys. We're going to sum those values together. And the products, it's going to be minus, oops, did I do that wrong? Nope, cool. Wait, yes. Ha ha. Reading out my numbers wrong. I apologize. One more time. So from the table, CO2 minus 393.5. HCl 2 times minus 92.3. That's our sum of our starting materials. The products, we've got COCl 2 minus 223.0. COCl 2. And we're adding to that one minus 285.8. The only stoichiometry we have to watch here is this value of our HCl here. So putting this together, starting materials works out to about minus 578.1. Products works out to minus 508.8. So the equation we're doing here, the overall delta H naught for this reaction is equal to minus 508.8 subtract minus 578.1. 8.1. I get 69.3. What are the units that are associated with this value? Yeah, kilojoules, or you can also write it another way, kilojoules per what? If we wrote this as sort of kilojoules per mole, what am I referring to? Remember last time we talked about, if I call this something like kilojoules, yeah, per mole of reaction, or per turn of this reaction. If this, all the stuff here gets consumed to make products, you're going to get, every time that this happens by one balanced chemical equation, requiring one CO2 or two HCl's, you'll get 69.3 kilojoules per time. So that gives me as D is the right answer for this process, right? Again, things to watch out for. Watch your magnitudes, watch your stoichiometry, watch your double negatives in terms of your points. The sum of all the products minus the sum of all the starting materials. Just make sure that your parentheses are in the right place. So that's how you can do it if you are given delta H's of formation. It's matching up individual values based on the delta H's that we've got. Sorry, one thing I want to quickly pause on. So Liza, we have Liza in the house today. Liza, can you jump off of your camera for just a second? Say hi to everybody.
Oh, yes. Good afternoon, everyone. I am TA that will be sitting in on classes. It's good to meet you all.
So Liza is the TA who's assigned to our particular one. She will be answering things in the chat. If I can't actually see it, you can get her attention as well. As we sort of move back to any other method of delivery, Liza's here to help out with the classroom stuff too. So by all means, if you need anything else, look forward to her. Okay. So we've got this value. Next thing. If we don't have delta H's of formation, Hess's law still applies. There's just one more way we can use it. Remember, a delta H of formation is just taking certain starting materials whose values we've defined as equals to 0. Their delta H's of formation are 0. So we're basically saying that the starting material energy content for those is 0. That makes the product values a number that we can actually measure against that. Yeah, Sam.
Hi. So you said earlier that we're using the kilojoules per mole. So if we had a reaction where it created like 2 moles of product, would we divide the difference in delta H or no? Okay.
No, remember again, the way we're defining this here is this is kilojoules per mole or turnover of reaction, right? So what we're saying is the balanced chemical equation as written above, how it's actually structured, equals this many kilojoules of energy once all the products are formed. It could be, molarity of 1, 2, or 3. If the next level down was, but I want to calculate how much energy I get for only 1 mole of product, then yes, that's where you would have to divide it down because you're putting it in context of a single molecular entity. But the convention as drawn here is balanced chemical equation, however it's written up there, we quantify it based on all of this starting material turns into all of these products. That's the energy per turn that we're dealing with now. Okay, but you could further, if I really wanted to say, but I want to know only the energy per 1 water, if it made like 10 waters or something. And then yes, that's where you could divide it out.
All right, thank you.
All right. So in the total generic sense, we can use this concept of Hess's law even if we didn't have just the delta H's of formation. If what we had was a series of any balanced chemical equations whereby rearranging them, we can eliminate or otherwise simplify it to give me that balanced chemical equation. What we're saying is this is the true sort of transitive property logic. Reaction 1, drawn here, A makes C and 2 E's. Reaction 2, F makes B and E, and reaction 3, D makes 2 F's. And we know something about those 3 values. So those are measured values that we've got based on our reference knowledge. With those known values, we've got the unknown reaction at the top. And if you notice, these 3 equations down here, some of them have elements that we do talk about in our reaction, A, B, C, and D, and some of them do not. E and F have nothing to do with the reaction we're looking at the top. So what we can do is rephrase these or create a balanced chemical equation by summing these unit sort of equations together to create the overall. And this creates a sort of just a general mathematical framework for solving these kinds of parts. Yeah, it's absolutely. This is just a substitution problem. So remember, the target reaction we're trying to build, A plus 2B makes C and D. That's the reaction we're trying to solve. What we're missing, or let's take them piece by piece. In the first equation, A makes C plus 2E, and that has some delta H1. Well, if you notice, A is a starting material. It's already in the right position, so I do not need to invert or change this equation. Drawing it forward is just fine. C is already a product. So we have sort of a representation. Not only that, my equation I care about only uses 1A, and I'm talking about 1A. So there's really nothing I have to do to this guy. It's in the right direction and has the right magnitude. I don't need to sort of multiply it out. Sarah, yeah.
So could you consider A, F, and D, since they are the product of two different chemical species, or yeah, I guess that's what B and E represent, or stuff like that.
Sorry.
Basically, would you rearrange the compounds to get the activation energy of the product? No, wait,
So,
I don't know if I'm making any sense.
No, you're making sense. Let me keep going. Let me pause there. Not activation energy. Remember, we're talking about the delta H. These are the enthalpies of these reactions. But yes, on that line. So let's say this first one, everybody agree? There's nothing we have to do to equation 1. It's kind of already lined up. We don't need to multiply it. We don't need to invert it. A and C lined up. The only thing that we're targeting, E, is a problem. But let's leave that for now. Let's move on to the next one. Next one, number 2 here. If I drew this F, B, and E, okay, well, again, B is something I care about, but it's on the wrong side. B needs to be over here. That's one part. And that's the only thing I need to focus on for right now. The other thing I notice is, well, I've got 2 B's. I need to multiply this by 2. So the unit operation I need to do here, to what was delta H number 2, there are 2 things I need to do. What are they? It's on the wrong side, and yeah, exactly. I need to make it negative, and I need 2 of them. The magnitude is wrong, and the sign is wrong. What I'm really saying is this equation should be written as 2b makes, 2b plus 2 e's makes 2 f's. And that would have the associated delta H of that process would be negative because I'm going the wrong way, and it's twice the magnitude because I'm taking 2 of them. That's my new reaction number 2. The nice thing about that is we don't have to do it yet, but if you see, look at what's happening. I've got a 2 here as a starting material, a 2E as a product. Those 2 are going to nicely cancel out if we were to sum these things together. So we're already on the way to sort of cleaning up our overall reaction. Last one. Number 3 is written as D makes 2F. And once again, we look, D is over here. It's on the wrong side. But that's the only thing we have to do. It's on the wrong side of the equation. Magnitude matches. So it's not delta H3. I need negative delta H3. That would be 2F makes D. And again, once we're set up here, that 2F is a starting material here. It's a product over there. This 2E is a starting material and a product. If we were to sum these 3 equations together and cross off things that are on both sides of those, starting material and product common, what we are left with is 1A, 2 B's makes a C and a D. We have the right chemical equation that's done by taking this here, the overall delta H of this reaction as summed by these 3 would be delta H of number 1 minus 2 delta H number 2 minus delta H number 3. Okay? So any chemical equation, any series of chemical equations can be manipulated, shift and slide puzzle, to match both the stoichiometry you need, the number of molecules, and the sign that we have to do. So remember, 2 unit operations are we can either multiply the magnitude or divide it, or we can change its sign by inverting those 2. So that's the 2 general operations that we can go through in this process. Every one of these problems, no matter how many equations, this is with 3, you could do it with 4, 5, 6, doesn't matter. But it's the same overall process to kind of evaluate through this. Yeah, Carmen.
Sorry, can you explain how in the second step you got a 2B, 2E, and 2F again?
Remember, the original chemical equation for number 2 is F, B, and E, right? I am the molecule I care about, the one I'm trying to look for, is my starting material, or my reaction I'm targeting has 2 molecules of B. The equation I'm talking about only talks about a single molecule of B. right? The original one is only 1 molecule of B. So I need to multiply this whole equation by 2, which means I'm doubling each of those values, and I have to invert it. It goes on the wrong side. Does that make sense?
Okay, so you're just trying to make it equal out.
Exactly. I'm trying to balance the chemical equation at the top by summing these unit little parts. Yeah, absolutely.
Okay, perfect. Thank you.
So that's the sort of the general process that we're going to go through for these. Thing I want you guys to practice, and this is in the notes. We can do this with any degree of complex equations. So who's heard of what's known as the bombardier beetle? Yeah, bombardier beetle is a crazy little insect. What it actually does is it produces the 2 starting materials you see: hydrogen peroxide, H2O2. It produces that quinoline species, the C6H4OH. It's a quinone type compound. When it mixes those 2 things together, it does a reaction. So it's taking hydrogen peroxide and this organic fuel, mixing them together, and you get this reduced product, or this oxidized product, C6H4O2, and H2O as a liquid. It's actually a ton of energy when you do this. For anybody who's recognized these molecules before, H2O2, where have you run into that before? Hydrogen peroxide, day to day, you may have sort of interacted with this. Yeah, cleaning, right? It's used for cleaning cuts as a pure thing. So who knows about things like the James Webb Telescope and things like that, the space kind of things? Hydrogen peroxide is this great, what's called a hypergolic fuel. You can mix it with things and they generally detonate or explode upon mixing. It's a ridiculously powerful oxidizer and used as a way for rocket propulsion. So the bombardier beetle has made this great little defense tool where it has the ability to basically use rocket fuel plus this organic molecule, do a reaction which produces a ridiculous amount of energy. So it actually has the ability to basically, it's got a bomb attached to its back end. Excellent evolutionary power. It actually has the ability also to use this like a jet. So it actually mixes them together to create this sort of jet of detonating material at things. It's an awesome little compound. But the point is, this is a highly exothermic reaction. The delta H of this reaction is massive. And if you wanted to calculate it, but did not know these things, or did not know the overall delta H, we have 4 chemical equations down below that you can use where we have known delta H's that rearranging, changing either their sign or their magnitude, we should be able to create the one up at the top. So those include things like water is a liquid, H2 to make H2O. So just by inspection, look at number 1, equation 1. Is it approximately the right sign and right magnitude? If you had to just quickly guess. H2O to makes H2 and O2. Are we in good shape? Yeah, because the thing we care about, H2O is a starting material as it is in their target equation. We're good to go. Let's move to number 2. The product of the second reaction is H2O gas. Our starting material is H2 and O2. What are your guys' thoughts there? Good to go? Messed up? Don't know yet. Is anything in that number 2 related to the target reaction? Or any of the species? Yeah, sort of would be the right answer. We don't use hydrogen, we don't use oxygen, and look at your product. Water's there, but what is the state of water in that equation? Water is a gas. We care about water as a liquid. So this one, that's one that's messed up. We're going to need it. Not 100% sure what you need to do with that one yet. You could put it to the side. The good news is water as a gas is kind of a product. H2O is a starting material, or H2 and O2 is a starting material. Let's skip it. We can't definitely right now know because it doesn't immediately relate to anything in the top one. Look at your next one down. Water is a liquid, water is a gas. Right sign, right magnitude, don't know. Which of these 2 looks good? Yeah, flip it, right? Water as a liquid is shown as a starting material in that space. We need water as a liquid as a product. That's 1. We need negative. What else? Does it have the right stoichiometry right now? 2 times, right? We need 2 molecules of water as a liquid. So we need a 2 and we need a negative. It will have a negative 2 value associated. That's good. So we put that one there. Last one, C6H4OH2, C6H4O2. Good to go. Magnitude, sign, flip. Yeah, no change. That's fine. So what we now know, first one's good to go. Second one, we're going to have to evaluate. Third one, -2, right? -2 times. Last one, good to go. The only weird one in the middle now is, so now that you know this, we flipped number 3. When we flip number 3, where does that H2O gas go? Starting material or product? Starting. And if you look at number 2, the weird one, H2O's gas is a product, it's probably good to go there. And remember, what was the sign or the stoichiometry we got from number 3? H2O gas, we're doing a... Yeah, we have to multiply that one by 2. That's all we have to do for that one right there. And minus, right? So it means that we need to double that one. We're going to have to leave it as it is, but double its magnitude in order to sort of cross it off. Exactly. So again, you can work through this thing stepwise, piece by piece, but the overall cancellation looks something like this. Middle one's going to be a double. First one's good to go. Third one is a -2 times. Last one's good to go. Cancel, cancel, cancel. 202 kilojoules. Would you think that is a big number or a small number? To kind of gravitate yourself, again, think about, yeah, per mole, per turnover, right? Every time this happens, you get 202 kilojoules of energy. I used to have, like, if you think about it, back in terms of our thing, that's almost the energy of our entire, like, remember our candy bar that we burn? That is a ridiculous amount of energy for 1 mole of this material here, and that's all contained in the back end of a very small beetle. This is a dangerous little bug, exactly. This is a ton of energy. So even calibrating magnitudes like this is a really good thing to kind of keep in track. But that's how you do this, right? Even in more complicated sort of scenarios. All right. Now, we've ended our thermodynamics. So thermodynamic part, or not thermodynamics, so the heat portion of it, the delta H and the enthalpy part of it. So remember, we talked about things being endo or exothermic. The reaction we just talked about now, endo or exothermic from this, right? In respect to the system, the chemistry, is this an endo or an exothermic reaction? Yeah, big time exo. Also the name of a very, very important K-pop group. That's how you remember this. So the point is, this is a massively exothermic reaction. If you look at this and we said, I'm going to do this reaction, what about what we call spontaneity? Being spontaneous, if a reaction will happen at all, is a separate question. So if we said a reaction is exothermic, does that immediately mean an exothermic reaction is spontaneous? And then the flip side is, if a reaction is endothermic, does that mean it's non-spontaneous? So this concept, spontaneous. Does anybody know in the topic of spontaneous, what does that mean in the context of chemistry? Well, yeah, we're getting to Gibbs. It's not activation energy. Spontaneous is a measurement of, in the world, in the physics and the thermodynamics and the rules that govern that part as it is, will that process happen if it is started? In other words, is it favored by the laws of thermodynamics? An example, we have 2 spontaneous things here, or a spontaneous and non-spontaneous thing to talk about. For example, if I take a block of ice at room temperature, first of all, do you know that in terms of heat, block of ice, with respect to the ice, at room temperature, is the ice melting endothermic or exothermic? Where is heat going as the ice melts? If I have a block of ice, it's in a room temperature, yeah, it'll be an endothermic process. It is picking up heat, right? But if I take that block of ice out of the fridge, put it on my desktop, will it melt? Would that actually happen? Would I see this and it's like, yes, that does not surprise me. Yeah, that is what we call spontaneous. In other words, if I just take a block of ice, it's cold. I take my room, my surroundings, it's hot. Heat will spontaneously move from where it is to where it is not. It is missing. There's a deficit of heat inside the ice. There is excess heat in the room. Heat will move, energy will transfer from hot to cold. That happens without anything else. It doesn't have to do this with rate. We're not talking about how fast it goes. That follows the laws of the world. Everything else, we're good. So yeah, that's a spontaneous process. And notice, it's still endothermic. Heat going into that system doesn't mean it doesn't happen. It just has to have an abundance of heat in the surroundings and less heat in the system, and it will happen spontaneously. It's still endothermic. The other side, if I take water and I throw salt in it, if it's not saturated, what happens if I take a glass of water and put salt into the top of it? Will it dissolve? Yeah, right? As long as it's not saturated, if I have water, I put salt in, the salt will dissolve. If I don't stir it, what happens? If I just put salt in the top and let it sit, will it eventually dissolve? Yeah, it takes longer, right? Same thing, if I take a glass of coffee, right? If I had a glass of coffee and I put a single drop of cream in there, will the cream sit in that one drop, or will it averagely spread out? This is what's known as spontaneous processes, right? What happens is, inevitably, if I take a solid and I put it inside a liquid and it can dissolve, not at equilibrium, it will approach equilibrium. Dissolution will happen. If I have a high concentration part of my solution, even if I'm not stirring it, eventually that whole system will slowly diffuse. It will balance out. Same thing with energy. If I put a lot of energy in one part of a system, it eventually will smooth or even out. Energy moves around here. This is our statements of being spontaneous processes, because we're talking about, and generally in the context of entropy, you guys may have heard something of, just disorder, right? What we're saying there is things generally like to even out or spread out or distribute to become a more even distribution of energy or matter within any space. If I had a gas balloon and I put a whole bunch of molecules on one side, eventually they will move around so that they are averaged out over the overall part. Those are spontaneous processes. With the example of the other one, I can't just take a glass of water and have spontaneously salt coming crashing out if it is below saturation. Even though that's an exothermic process, heat is released when we crystallize things, it doesn't immediately happen, because that would mean suddenly, for some reason, all the salt decides, you know what, I'm not dissolving anymore, I'm crashing out a solution. If we're at a certain temperature, pressure, it will not happen there. A lot of a good measurement of, is this spontaneous, is kind of a gut check of the world itself. So, has anybody heard of a kinetic model using things like these kinetic things like these stick models and stuff? So watch what happens here. We raise this stick, hold it, and drop it. It's a pendulum, but notice the arc of this pendulum. What happened there? Something doesn't look okay there. And now it's flipping over the top. And now it's going full 360s. Does something look wrong about this video? Oh yeah, it's a double pendulum. That's not good enough. What looks like happening here is, remember, if I raise this thing to some height, the best thing I could ever do is full return of energy in a perfect pendulum system. What's happening here is, it looks like at certain points you're getting more energy back than you have. So how does this work? What's missing in this thing? This is almost a visual of perpetual motion. What's missing about this description? The battery. In these kinetic models, and this is my best statement I've ever heard. I think it actually goes back to some of the cool inventors like Tesla and whatever. The hardest thing about making a perpetual motion machine is where to hide the battery in the motor. The thing that you're doing here in that example is in the base of these models. Usually there's an electromagnet with a battery, and every time the pendulum passes it, it's giving it a goose. It's actually adding energy to the system. That's how we're beating things like, well, why would it slow down? What would your expectation be for a system like that? We'd expect it to eventually slow down. Why? Not gravity. Gravity is the thing that's driving it. Friction, right? There's loss. The fact is, if I put a ton of energy concentrated in that system, the universe says, that's nice, but there's a tax, there's a price. You will never get 100% return on energy, because friction is going to lead to heat, which is going to erode the energy of the system. And eventually, where does that heat go? If this was my room and I'm letting that system sort of swing, where does that heat go? Into the air, into the room, starts with the U, the universe, right? The surroundings. Energy will constantly be dissipated out, and that's the nature of what the world that we exhibit. We were used to this idea of non 100% return because there's these inefficiencies that are involved in it. This is the second law. The second law, first law is awesome. We have conservation of energy. That is wonderful, and that is true. The second law is the downer. You will never get 100% of what you give. That's this inefficiency of kind of return. So we need to talk about a quantity, a way of measuring how much, or the concentration or distribution of energy inside a system. This is what we call entropy. Now, you've often heard of it as the randomness or disorder, where really what we're talking about is, again, by order, what I mean is if I concentrate all the energy in, let's say, a hot spoon or something, it's concentrated here, but it will spontaneously, in contact with something else, the energy will leave where it is concentrated and move out or spread out. A coffee cup with a drop of cream that is a ordered system will move to a disordered system. The molecules will spread out or even out in distribution. That is the nature, and that is what makes sense. This is also, people, you may have heard this, entropy is referred to as time's arrow. If you watch a video and it makes sense to you that things are going normally, things are happening the way you expect, that you lift an object, you let it go and it drops, that is a normal expression of how entropy is working. If you're getting the opposite happening, where suddenly a house of cards springs up and then sits as this perfectly ordered event, that looks like, wait, that feels wrong. That's because you're watching in a reverse sense. You're not obeying the second law. You're actually looking at something where entropy is being violated in that sort of case. We have this general principle where we measure entropy as changes in entropy where increased disorder or increased spreading out of energy leads to a positive delta S value. Whereas the other side, the ordering of system or the compression of energy or ordering of matter leads to a negative entropy value. So these are how we assign our signs, and this is generally the concept that we're kind of going into. And again, what's weird about entropy is we sort of just kind of get it from a perspective of, yeah, that makes sense, and it also sounds very abstract. So we're going to really focus in terms of chemistry on these kinds of things. In general, we can quantify entropy. We're going to do it from a delta S value like we did with delta H. But the principles are, look, if we increase the temperature of something, entropy will generally go up. As we increase temperature, the entropy in that system will generally increase. And that's just because how we're distributing the energy, how we're spreading it around the system will generally increase. Pure liquids in contact with a pure solid, they will dissolve, they will mix, they will form different materials. So forming these solutions is another expression of increased entropy. Gases generally will have a higher entropy than liquids. Liquids will have a high energy than solid. Why would that be? Just focus on that one. Why would a gas have a high entropy value as compared to a liquid or a solid? What's one way you could say that? Yeah, Sarah.
I believe it's because the entropy is the measure of chaos in something, but then again,
No.
why does it increase while molecular complexity increases as well?
Right, so, but you're right, it's kind of a measure of chaos, but think of it like kind of like bins. If I'm a solid, and I was going to try and take the same amount of energy and distribute it in that solid, there's not a lot of freedom of motion, right? It's basically a crystal lattice that kind of can wiggle around. Liquids, since they're more fluid, there's more ways of smearing around the energy and distributing it in a bunch of different orders of geometry. Solids are very rigid, they're very well aligned. You don't have a lot of choices of how you want to sort of spread out your energy. Liquids, they can kind of slide past each other. Gases, they're flying all over the place. We've got lots of different ways of sort of spreading it out. So you can think of it like if energy had to go in buckets, solids have very small buckets, liquids have bigger buckets, gases have huge buckets. So we can spread them out more.
Oh, so basically you can put it all in one bucket.
If you needed to,
gases,
right? You have the in statistical mechanics, we say there are more microstates within the macro state. There's more options of how we distribute it out when we're dealing with sort of a gas, just because there's more molecular freedom of motion there. Sorry, yeah.
What do you mean by molecular complexity then?
Molecular complexity is talking about, so a non-complex molecule, sodium, right? Just an atom. If we were trying to distribute the energy in sodium, all we can really do is it can bounce around more. Maybe we can change the energy of its electrons, but we don't have a lot of other degrees of freedom. That's kind of all we do if we have a single atom. If we had a molecule like caffeine, that's a lot of atoms that have a lot of bonds. Each bond can vibrate, they can rotate. We have so many different ways of taking the energy instead of just, it's got to be held on this atom and the atom can fly around. It's really, I have translational energy and I have maybe electronic states, that's it. As molecular complexity, more atoms make these larger molecules. We now have rotation in the molecule. We have rotation of the overall molecule. We have bending, flexing, rotation. There's a lot of different ways that energy can be contained inside that much larger molecular structure. There's more orbitals that are involved with many more atoms as well too. That's what we mean by generally molecular complexity. Bigger molecules.
Right,
More atoms involved. Yeah, diatomics are going to be more complex than monatomics, exactly. But we generally with complexity, and this is a minor point, like it's the smallest of our sort of knobs that we have here. In general, on this list, in terms of sort of quantitative values, gas, liquid, solid is the biggest one we have, as well as temperature. Low temperature, very little entropy. High temperature, lots of energy, and the same entropy, excuse me. And the same thing with this phase distribution. Going from a solid to liquid to a gas is the largest delta S's involved with those ones too. So those are our biggest ones we can definitely work on. So if you look at this, what do you think? Is this process, as we described here, an increase in entropy or a decrease in entropy based on the concepts that we just talked over there? Let me relaunch. Okay, let's go 10 more seconds. Yeah, it's in equilibrium. All right, and we'll go time. So, B is the winner by popular majority. I agree with you. If you look at this, again, what are your qualities of evaluation? What would you say, based on what we see here, on the list we just talked about? What is changing? Moles of what? Well, we go from 1 mole of nitrogen gas and 3 moles of hydrogen gas to make 2 moles of ammonia, right? You're right. What's happening is not just moles are decreasing. We're going from 4 different molecules, right? 3 hydrogens and 1 nitrogen, and we're making 2 ammonias. So yeah, the overall buckets of energy, the number of moles of gas in particular, we start with 4 moles of gas in the starting material. If these are all ideal gases, we treat them the same. They're all ideal diatomic gases, and we're making 2 moles of a product. That means a general net consumption of moles of gas. If this was a balloon, we'd have a smaller delta V, right? It'd have to get smaller if we did this. So yeah, this would generally be a decrease in entropy if you looked at just moles of gas. What are the other things too? There's no energy. We did talk about temperature here, so we can't use that as a rank. One of the things that people look at this too and goes, well, wait a minute, hold on there, Bi. Yeah, the molecular complexity is increasing. And I agree with that a bit, right? A diatomic, and a bunch of diatomics is making this overall here. The difference between them too, what we call molecular complexity, you're absolutely right, there's some, but there's a price that comes with that too. Breaking those hydrogen-hydrogen bonds, or the nitrogen-nitrogen bond, that's a triple bond there too. Part of it is, okay, yes, we are making a slightly more complex molecule, but on the magnitude scale, molecular complexity is, think of it as like 1 to the power of 1. Gases to a liquid or liquid to a gas, those phase transitions have a much larger magnitude associated with them. Molecularity complexity is usually the smaller handle, the smaller number between these two. So that's why we're discussing it in this sort of context. Watching your number of moles of gas is absolutely a big one. Temperature is the other big one. What do you think about this? For which of these processes would you have a negative delta S? Okay, 10 more seconds. All right. And time. And crushed it. Yes, B absolutely is correct. If you look through these, right? Evaporation of a liquid, we are moving from a liquid to a gas. That's a generally increase. And not only liquids have less entropy than gases, so we're increasing there. Melting of a solid, that's a solid to liquid transition. Again, that's a positive delta S. Sublimation, what does that mean? What is a sublimation process? What to what? Solid to a gas. Absolutely. Freezing of a liquid is the only way we're going from liquid to solid. We're stepping down. No matter what temperatures these have, just that initial phase transitions, focusing only on these, we'd expect B to have a negative one, which would probably have the biggest positive delta S. If you had to guess amongst these, yeah, solid to a gas, you're skipping the whole thing in between. Generally, a sublimation process is going to be a massive delta S. Okay, so why does this matter? This is what we call, or sort of framed in context of the second law. What we're saying is, well, the first law talks about how energy is distributed. Not violating the first law makes it physically possible that something could happen. We're looking at energy must be balanced, and that's a way of saying, okay, if I give up this much energy here, I will get this much energy over here between heat and work. That's the concept or framework we talked about with the first law. The second law talks about if a process will happen spontaneously, meaning it matches what our description of where energy will move once we get a process moving, right? So this is the flow of energy from high to low, or from generally from a more ordered to less ordered state. Those things will happen spontaneously. The trick with this is we have to remember that the principle, the most important thing for the second law, is we're not talking just about entropy of a small thing, maybe the system. There's a bigger one too. Does anybody know what we're really caring about? If you've heard in terms of entropy, what's the thing you must never violate? Delta S of what is always increasing? You may have heard that sort of thing. Yeah, the universe. This is a summation problem. So we'll talk a little bit more about this too. There are processes. For example, we just said, of these things, which one is negative? Freezing. Does freezing happen? Like if you actually set up the system, can something freeze? Yeah. You just need to have the right system around it and the right system and right surroundings for this process to happen spontaneously. So you can set the thing up. But even in that process, the statement we're making is there's still an overall price, and in general, the price is always greater. The cost is always greater than what you return from all of these things. There's always a non-equality involved here. And this is the thing like we say with the losses of energy due to heat. But generally, spontaneous processes will happen once they start, and that can be the flow of energy from a hot thing to a cold thing, so system to surroundings or surrounding to systems. Non-spontaneous processes do not occur unless you're constantly doing something about it. You must modify the system in such a way, or the surroundings, for the process to occur, in which case it becomes a spontaneous process. This is really a definition of which way energy is going to move. And again, what we're really saying is if I had a hot thing and a cold thing, it will only move from hot to cold. If I really wanted to go the other way, I've got to change where that energy distribution actually is. But stated mathematically, the second law of thermodynamics is kind of like inequality. Overall, system and surroundings are still related to the universe, but more importantly, the universe, it's this not just, universe is greater than or equal to the overall sum between the two. In other words, for most processes focusing on just the system, the surroundings is going to have a bigger price if there's something that's in between these two, or vice versa. The system is going to pay more, the surroundings is going to pay less, but the overall delta S of the universe must be a positive value. This is also sort of the inevitability of time too. We're moving towards a single point where there's a finite end to all things in the universe as energy starts to distribute out in this particular way. So yeah, there's a sobering thing for a Friday. Yeah, heat death of the universe. That's right. But what we're really saying, again, having this value, it's like that all processes, time has a ratchet, that there's a single direction of motion of that thing that is obeyed according to the second law. There's nothing that's absolute perfect efficiency is kind of really what we're sort of stating through here. So we break these things up where if the delta S of the universe is a positive value, that is what we normally experience, we consider this a spontaneous process. That's where energy or matter is moving in a direction for a process, and it will happen once that sort of process occurs. Once we start with a hot and a cold thing, we put them together, heat starts to flow, there's nothing else I have to do besides setting the system and surroundings up. In a perfectly reversible system that is maintained at equilibrium the entire time of that process, the delta S of the universe can be at least zero. That is a possibility theoretically. We've talked about this part before. What is, given the examples we've discussed, what is an example of a perfect reversible system that might fit that middle criteria? Something else we've discussed. Yeah, the case where W equals Q, that was what? That was, what do we call that? Special iso something, isothermal. What were we talking about though in the context of that system? That was, starts with a P, isothermal. Yeah, it's our piston system, right? If we have isothermal compression or expansion where we do it infinitely slow, where heat and work are perfectly balanced, that's the best example we could have of this nice reversible process. And in that case, there's no loss because all the heat becomes all the work. What we acknowledge, though, is in normal everyday life, any piston obeys the first case there. Delta of the universe will always be greater than 0. And the reason why is heat or work in a normal sort of operating piston will have these times where during that compression or expansion, it is not in perfect equilibrium. There's going to be extra friction involved, and we're usually going to see a general loss that's involved in that point, okay? The last one, the delta S of the universe being negative never happens. That's going back in time. That is an impossible process, okay? So these are sort of our 3 brackets. But what this means, though, is that like what people sometimes interpret that last one is, oh, delta of the universe is negative. That means that nothing that has a negative delta S could ever happen, or an ordering process could ever happen. I studied crystallization. Crystallization fundamentally is taking something that was in solution and creating this nice, perfect crystal lattice. What do you think the delta S is if I take something that was dissolved and turn it into a perfect crystal? It's probably going to be negative because I am ordering it. I'm taking matter that used to be nicely floating around, happy and free. You know, it doesn't have a summer job, doesn't have to go and teach. It's great. I'm not registered. Oh, now we're locked up and we've got this perfect ordered crystal. Yeah, it's going to be a negative delta S associated. But it happens. Crystallization can happen. What about, have you guys, anybody in biochemistry, have you studied what's called the hydrophobic effect, right? The hydrophobic effect is another expression of ordering. We're saying that lipid molecules in a water environment will spontaneously form these nice ordered layers where all the lipids like to line up and stack up in a nice ordered membrane. Those things do exist. They don't violate the second law. What's happening in cases where there is an ordering, the delta S of the system or the surroundings can be negative. All we're saying is there has to still be this case where the universe still gets a bigger piece of the pie. If a system has a negative delta S, that means that the surroundings needs to have a larger positive delta S, where the magnitude of it is such that the overall universe still wins. It's still bigger overall, that the sum of those two. Right? So this is a combination of those two parts. It is not impossible for the system or the surroundings to have a negative delta S. The universe is still going to be positive because one of those two things has to give in a non-equal way. So the last thing we're going to mention, what we're going to leave off today, is the molecular or the mathematical definition of entropy. Just like we did with enthalpy, with heat, we needed a way of saying how much heat energy is somewhere. And for that, what we discussed was we have the delta H of formation. We just created a common state. We say that all elements in their common, in that common state, their delta H of formation is 0, and that way we can compare everything, all molecules, to this common state. Now with entropy, we do something slightly different. Boltzmann wrote this equation, and the only thing you have to recognize on it is that what he's saying is, in any object, S, the entropy in this object, is equal to, proportional to what he called K, his constant, the Boltzmann constant, and the natural log of W. What W is it's basically a measurement of how many ways we can bin energy, how many ways we can distribute energy. It's really related, you can think about it related to temperature. If something is very hot, we've got a lot of different chunks of energy, we can bin it around, but as I cool things down, my W value gets smaller, 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 smaller. At absolute 0, by its definition, W equals 1. That's part of this concept that there's only one way to actually organize energy when absolute 0 is hit. When all molecular motion ceases, W is what he calls the number of microstates. It's a value that he sort of divides through. So what does that mean? If I said W equals 1, what happens to that equation? logarithm of 1, which occurs at absolute 0, what's the value for S? Goose egg, right? He defined this because what he was saying is, wait a minute, ways to bin energy has a temperature component. As things get hotter, W gets bigger. As things get colder, I'm going to put a line in the sand and say at some temperature such that the number of states, perfect crystallinity is achieved. That's the temperature where S for all material is also 0. So we put a threshold down and say, this is our reference point. At absolute 0, at temperature on the Kelvin scale is equal to 0, W is equal to 1. Therefore, entropy of all things at temperature equals 0 degrees Kelvin is also 0. That's kind of why the Kelvin scale is what it is. It is an extrapolated value to say how cold would I need to go for all molecular motion to stop. It's based on this kind of a principle. It's not that we've come really close, but it wasn't something somebody put a temperature probe in and went, oh yeah, I guess it stopped, minus 273, there you go, that's it. No, this was a calculated value based on this concept of proportionality, right? So this is our floor. Remember, for thermic values, for delta H, we use elements in their standard state. Their heats of formation are 0. For entropy, we say all matter at temperature equals 0, its entropy is 0. What that lets us do is say, okay, I can take any molecule at normal room temperature pressure conditions and I can measure the standard molar entropy of this value. It's kind of like the delta H of formation. And once again, it's going to have a table. Every molecule will have this value that we can have. And then just like Hess's law, if I know something about one molecule and I have an equation, an overall formula I'm trying to solve, I can solve the delta H of it. It is a value that we can kind of put through. Again, quickly point, remember, what we're saying down there at the vertex, at S equals 0 and T equals 0, that is absolute 0 on our temperature scale. As I warm something up, the solid portion of it will have a gentle slope. It will increase with temperature. Then we go through melting temperature. We go through a phase change where there's no change in temperature, but the entropy is going to jump. That's as we go from a solid to a liquid. Now, as we go through a liquid, you notice the slope is steeper, so changes in temperature in a liquid have a bigger jump in entropy than for solids. And then finally, we go through our last temperature, our phase change, boiling. And once again, no change in temperature, big jump in entropy. And then finally, gases are up the top. But this is meant to ground you of like, why does temperature matter for entropy? That's why absolute 0 is equal to 0 on the scale, but also the magnitude changes. Gases are way separated in terms of entropy than solids. We can use the same idea. If I know the final and the initial, I can sum this up and measure based on exactly what we did for Hess's law, what the overall delta S for some process was going to be. But again, I need to have these reference values where if I have the delta S of all my products, my delta S of my reactants, the sum of those values, just like we did with delta H as a formation, will allow us to calculate this. Okay? So we're going to stop off here. We'll do a couple of questions and calculations based on this. And then from there, we're going to jump into our kinetics chapter.